Digital logic is what we use now in our circuits. All our devices are digital, and there's lots of mathematical operations that happen based on these basic logic devices. So we understand the logic to be uh, whatever is the input and whatever is the supposedly the output. For example, an inverter is where if you give it a 1, it gives you a 0 at the output. If you give you 0 in the input, it gives you 1 at the output. So that's an abstract high level kind of looking at gate. We call them gate. And a goal here is to now connect that gate operation with the actual electronics implementation. And so using our knowledge of diodes and transistors, we're going to translate now it into a gate, and ultimately a logic that we can implement. So when you say logic, here are some very basic examples of logic. So we have OR circuits where if one of the inputs is high, the output is high. And if there is no input is high, this is 0. So we call that OR, right? Either or, if you connect it to a normal language that we speak. So AND is where then the output will not be high unless both of the inputs are high. So the output has direct relations. So as long as one of those, at least one of the inputs is low, the output will be 0. Now you have to see these two tables are taking into account only 2 inputs, but they can be 3, 4, n inputs. The behavior of the gate would, or the logic would stay the same, or requires at least one of them to be high to give you high, and requires and would have a low input, low output if any of the inputs is low. So we put them into what you call truth table to understand whatever we want to do. Now this is, we are building on top of what we have learned so far. And the next step is then the circuit design, VLSI circuit design, where they would do chip manufacturing. So we will not go there. What we will do is, this is up to where electronics comes into computer engineering, knowing what is the need of a gate or a component and how do we implement that? How do we use electronics to get that output from there? Now, if you know OR and AND, then the flipping them, putting an inverter would give you opposite results. So for OR, at least one of them had to be high to get output as high. Now, at least one of them have to be high to get low output. So what we have done is we are inverting the output from there. So if you can connect the output of this guy, you see that this is nothing but just flipped version of or inverted version of that. And similarly for NAND, so the N would tell us that this is nothing but the inverted output or outcome from what you would get from an AND. And we saw how we can implement it using simple diodes, using the forward bias or reverse bias operation, and looking at what voltage exists on both sides of a diode, we can see how it gets implemented. So in this case, then D1 and D2, you have input A and B, which can be low or high. So when it's low or high, there's a reason we don't use actual voltages, because the real world implementation would depend on what kind of voltages are there. On desktop computers, it used to be 0 volt and 5 volt, but now the smaller devices, portable devices, the low is not always zero. It is some baseline, and high can be 1.1 volt or 1.2 volt. So we just stick to low and high instead of actually putting the voltage. But we do have a notion of what kind of voltage is there on the power supply and what kind of voltage is shown. For example, here we have shown 5 volt and 0 volt. So two discrete levels between those two. So this is implementation of AND. In a similar way, there's an implementation of OR. It's an OR gate. At least one of them have to be high to get an high, right? So, and then to get maybe NOR or NAND, we will look at that. How do we get other logics out of these basic components? Now, if we have nailed down our Nmos and Pmos and diode and their biasing, we should be able to put them in different combinations and implement a logic out of those basic operations. And let's revise that. Let's put them together before we start making some basic circuits, basic gates. So ideal inverter is written or drawn like this. And so there are power supplies, and there's input and there is output. Here we are again looking at abstract level or high level picture of what you would expect from an inverter. And we say ideal because there are always transfer characteristics, as we saw in op amps or diodes. Yeah, we have ideal situation, but then when you are looking at the real application, there are some issues and changes that we have to know as designers. So we'll get into that as well. For inverter, it's as simple as that. If the input is high, the output is low. If the input is low, output is high. Now we have to now remember what is the basic operation of a transistor and how would that come into achieving these goals. So let's put down some basic ideas of Nmos and Pmos, what happened in both cases. So if you just remember these or find a way, make some mnemonics to remember that, it's going to make our life easy. So we write our transistor Nmos. Okay, I always remember N negative. If you don't like negative people, you push them away. We always push the arrow outward, right? That I also have to remember how do we, if arrow goes in or arrow goes out. If you are positive about people, you like them, you invite them, arrow goes inside. So if you think this way outward, yeah. So now you see, so in one case we put arrow lower side, on the other case we put the arrow because that's the direction of current, right? So we have, in both cases, we have different ideas of where current flows. But now we'll take this, the characteristics of Nmos and Pmos, and we will use that into whatever we'll do. For Nmos, we have to apply gate voltage to make it work, right? So we have to make the gate high to make it work. It has its drain and source resistance, which we knew for small signal, that was RDS. But generally we know that when gate is high, the current conducts. Current is good to go between source and drain, right? So which means that the power supply, which is generally right down on this side, would be would be traveling to the other side, so we'll get the signal on the other side. Now for Pmos, it has the reverse operation. Okay, so here, and if the gate is low, 0 volt, there's no current. Or we can say I equal to 0. Now for Pmos, it's the complementary fashion. To turn it on, the gate voltage has to be low, right? So remember that the VOV and VDS relationship, or VOV and VSD relationship, so it has to be low. When it is low, the signal goes through. So there is this line. So and conversely, if the gate, don't take it as, so let me just put VG with this. So gate voltage is high, it's not conducting. So there's no signal, no current goes through. We have to remember this by heart, because this is the fundamental information which we will look at the implementation, or we will implement based on this knowledge. Now, when we see this, we can see that the gate voltage is what is being used as the controlling node. Right? So let's look at an example from the book. So that's 16.1. Oh, sorry, example 16.1. Let's hold on to it. So there is another idea that I want to discuss before we do that example. So in both these cases, when we have Nmos, when the gate voltage is there, we would have a signal between source and drain. And if there is no gate voltage, we would consider it to be an open circuit. So when you're controlling, that's the situation in both cases. So we have to know for Nmos, high at the gate means high output. VDD is always going to be there. So power supply is always there. It's just that we would control if the output would be, what would be the relation of the output with respect to the input. And you turn the gate voltage off, you get 0 at the output. And for Pmos, this is reverse. So to turn it on, you have to bring it low. And if you do have gate voltage, then this is open circuit. So flip operation for both of those. Now, if you know the switching behavior, we can create an inverter out of this. And what it has to do, it just has to invert the logic value of the input signal. So we would write it as y equals x bar. So if I make my circuit, what do I have to do is my input has to be switched on the output. And that's my truth table or my Boolean logic, Boolean expression for that. How do we implement? So that's, you would have power supply always there. You have Pmos, you have Nmos, and there, let me, so we call this Pmos. This is our Nmos, and this is where we get our output. So this is input and that's output. So they both have their own operations, and the gate is connected, both gates are connected to the input. Now, if you think about input as 1 or input as 0, and we'll see what would happen. So on this side, both drains are connected, which are connected to the output. So when the input is high, say we call it 1, in that case, this guy is equal to Vx is equal to VDD, which transistor will be operating and which one will be closed. So if the input is high, which one would be conducting and which one would be open circuit?
So if there's high on X, then the Nmos would be active and VD would go to ground.
Exactly. So if Qn is active and Qp is open circuit, what would happen to this signal or this voltage? Just go to ground, right? What would you get at Y?
0 or low.
0. Low, right? So in this situation, Y would be 0. When X is equal to 1, which is this situation, in that case, your Y is equal to 0. Now, if X is equal to 0, which means low, so we can see transistor N would be open and transistor QP will be conducting, right? So if you look at the signal, which way it has to go, this is open circuit here. It cannot go there, so you will see the output at Y. So your Y will be 1. Are you guys with me on this? So here, if you were to make notes or show your work when you would be given something like this, so you have to know, or you have to identify QP is, you can find either way. You can say QP is not conducting and QN is conducting. So it's, you write it down, or you have to show somehow what is your understanding of what's going on there. So, and in this case, QP is on and QN is open circuit, right? Or you can say close or open C or whatever way you do. But the idea is that looking at the situation here and identifying what transistor is in what paths, our nodal analysis will tell us what voltage we expect on that output node. All right. So now if I make an alternate circuit of this, or its operation in the form of a circuit, I can just show these as resistances and or open circuit. So you can show the situation where you have the resistance of diode, which we can, in this case, this is open circuit. So what situation is this guy? This is when X is equal to 1. And here is what we call, so if you remember, we had this small VDS signal when we were doing MOSFETs. This is something we write as RDS. So we can find out this resistance on what would be its value. Right, so here they say they're writing R on in the book, but this is the same thing what we have studied before. How do we find the drain to source resistance if we have to? But it's our signal is all, input is all getting grounded here. All right, so in similar way, if you want to show the input as small, so here then you would show the resistance of this guy, and this will show as open circuit in that case. So which means then we are getting signal here, and that's the case for inverter. So that's a simplified implementation of an inverter with two MOSFETs, N MOSFET and P MOSFET. There can be other ways, but this is the most simple way how we can implement that. Now, if you look at it, or if you think about it, in one case, the Pmos is what is pulling up the voltage here. So it's providing the voltage. So we call this as pull-up transistor. And if you think about this guy, so this is bringing the voltage down. We call this you have to find your own wave. The way I understand, or the way I remember it, that when the gate voltage is high, Nmos is conducting, it's getting the signal through and down to the ground. So it's pulling the signal down. But in case of Pmos, if I apply the gate voltage, it's open circuit, it's pulling the voltage up. It is not letting it go through. So we call them, and that's another way of referring to them. We call Nmos as pull down transistor. And that's Nmos here in the inverter circuit here. And Pmos is pull-up transistor. So what the idea is that the gate has then two networks here. One is PDN, pull down network, and the other is what you call pull up network. And in the case of this inverter, now you can then, instead of writing, this was one input, right? So they can be A, B, C output. So then you can just write, instead of writing all those transistors, we can write down as the Pmos side to be as pull-up network with the output connecting with pull-down network. And here again, there can be multiple inputs. And we can simplify that the breakdown of bunch of transistors as a big high-level block diagram where you can show the two networks which are working on a number of input variables in a complementary way. So for 3-input gate, the PDN will conduct for all inputs that require a low output, and that would cause the zero output at this point. And for when the gate is high, that is when we will get the pull-up network working and resulting this to be low in that case. So in PDN, we have a lot of they are comprising of Nmos, and these are comprising of Pmos. So they can also be used to form an OR function. And if you use pull-down networks in parallel, we can get an OR function out of this. Again, we remember that OR means at least one of the inputs have to be high to get an high at the output. Or we can use them in series to form an AND logic. Okay, so think about it. And if we know where does the pull up or pull down come from the high gate voltage would make an Nmos conduct, right? A low input on Pmos will make it open circuit. You have to just remember it, grind it down, because that's what then gets into this idea of how does it translate into an AND or an OR. So PDN in parallel would form OR, and PDNs in series would form AND. So in parallel, one input would result into one high would result into high at the output because it will be conducting. All right, let's see the implementation for a circuit which is given where you have your output. There's one input here. One input here. And they are at the ground. And this is QB. And they both are N-type. And this is QA. All right, so of course there's VDD power supply. Now let's take a look at this. If now we have two inputs. If, let's take all situation, if A is 0 and B is 0, what do we get at the output? If A is 0 and B is 0, what do we get at the output? Okay, what kind of transistors are we using here?
Pmos.
All right, so arrow direction. If you don't like someone, we have negative feelings about somebody, what do we do?
Nmos.
Push them away, right? So,
Y would be 1.
all right, very good. So what kind, okay, Aristo, thank you. But let's nail down few steps when how we get there. Arrow tells us what kind of transistor is this. If you like somebody, you are positive about somebody, you say, hey, come on, let's have some food together, let's have lunch, right? So that's arrow coming inwards. So for Nmos, 0 volt means what? Gate 0, gate low in Nmos.
That means it's closed.
Which is closed, right? Hold on. Nmos 0 at the gate means closed or open?
Closed.
I'm going very slow here. Let's go back. So for Nmos, 0 at the gate means what? Open or close? So this was for Nmos here. What kind of circuit is Nmos with 0 volt? It's open or close? Just say it for posterity. Is it open or close? I know you can say it's open.
Closed.
Hold on. Nmos gate 0. I have an arrow for high to be closed, but for gate 0, I have arrow towards something which is open. So this is closed, this is open. All right, let me ask again. For Nmos gate to be low, what kind of behavior it has? Open or close?
It's open.
It's open. Right? Yeah, I'm okay. That's why I'm going slow. We need
No,
to.
I got confused with the closed, thinking like there was no current going through, but like
Yeah,
it's the opposite.
Yeah, in circuit, close means the switch is closed, the current is flowing. I know exactly what you're saying. That's why I wanted to get the vocabulary right, so we all talk the same way. So close always means the switch is closed, the current is flowing. Open circuit means open, which means there's nothing flowing there. So I know you were saying the right thing, just wanted to get the vocabulary right. All right, so now let's take a look at it again. A is low, B is low. What are these two transistors doing?
They're both
QB
open.
is open, so I can say it's down, and QA is also down or open for, I don't know how to differentiate O from 0 here. So which means, what is your output? High or low?
High.
High. Okay, so Y is 1. Now let's change one of the inputs to be high. So just want to stay here in some corner. So I say A is equal to 1 and B is equal to 0. What do we get here? So one of them is high, one of them is low. So yeah, we can say B is equal to 1 and A is equal to 0. So when that happens, so one of them is conducting and one of them is not conducting. What happens to the signal?
It goes to ground.
So signal is 0, right? It's low. Sorry, output. So output is 0. Now, what would happen if both are high? So they both are open or closed? So
They are both closed.
they're both closed. They both are conducting. What happens to Y?
Equals 0.
Equal to 0. What kind of logic is this? We have to get back to our truth tables.
A NAND.
It is, okay, so at least one of them has to go, like we were saying, at least one of them has to go high to get the output 0. So it's NAND, inverted of NAND, right? So we write that as, so this is AND, right? So multiply. One of them has to, but NAND is we put the bar. So this is the logic from this circuit, right? So I hope today we can say, okay, why we were doing everything that we are doing so far to get logic circuits out of those. And then we take VLSI course and then you use these to make some chip level designing. All right, so far so good. Just one example. All right, let's look at another example. Now, the Boolean algebra has this association kind of thing that this can be, sorry, I wrote it the wrong way. This is not the way. So the idea is that you multiply them, the output is inverted. The bar has to be here. Now this can be written as, so this guy can be written as there is, and we'll pick this up as we go. The Boolean algebra associative, or what are they called, the properties where you can, how we can convert them from one way to the other way. But that was, I had written that on the first slide where we had the De Morgan's law, De Morgan's rules or laws here. This guy. So which connects our AND with OR and ORs with ANDs. How do we can take the union, which is OR, and convert it into AND, which is what is that? Union and intersection in maths. So those are what can help us take or implement one logic or one circuit to get the other logic, which is the same thing, but yeah, you can write it like that as well, which just means the same thing. If we were to go through those from here, we'll get the same thing. All right, so far so good. So we were using both Nmos, we were using PDN, right? So we are just using, we are showing one transistor here, but this can be multiple of those. So they can be multiple inputs here and multiple inputs there. So this might as well as we start calling them as PDN and PDU, right? So just remember pull down network and pull up network. So Nmos, call it pull down transistor or pull down network, and Pmos we call them pull up transistor or bunch of them pull up network. So here what we have used is pull down network to implement these logics. And there are more than one ways to achieve the same logic, right? So if you see something, you should be able to, from one logic circuit, you can see that it can be implemented another way to achieve the same output. All right, let's look at another example, which is two transistors in series. And my arrow tells you what kind of transistor am I using or what kind of network I'm using. So that's my A, that's my B. All right. So is it pull up or pull down? Are these pull up networks or pull down networks? All right. Another mnemonic. Negative people bring you down. Right? So Nmos is pull down. Right? Positive people cheer you up, bring you up. So pull up is Pmos. And it has to do with the inverter circuit that I showed, where we saw that the voltage, high voltage makes it conduct, signal goes away, you get zero. So we call it pull down. All right, so it's just terminology, and there's a logical reasoning of why we call them what we call them. But you have to, from one transistor, then we have to start thinking of a network instead of looking at each transistor. So we have the network of Nmos and Pmos, and we call Nmos as pull down. So what kind of signal we get? So let's say A is 0, B is 0. What do we get?
Y equals VDD or Y equals 1.
Y is equal to 1. Very good. So, and if I have any of them 0, what do we get? Any of them 0. So it can be A is equal, sorry, A 0 or B 0. What do we get? So
Y equals 1 still.
Right. So Y is going to be 1 in, even if you flip them, is going to stay 1. Right? So for Y to go 0, what's the requirement for Y to be up? Oh, sorry, Y to be 0, both have to be 1. Right? So in that case, you'll get 0. What kind of logic do we see here? So think about it. They both have to work together to have a change here. So what kind of logic is this? All right.
Would it be an OR?
You have to take a step back. So one thing is, okay, so they both 0, we get 1. At least. So it's and yes, and flipped of and. Very good. So if I have to write it down, and is A times B. sorry, I think I missed. So hold on. This was at least, so yeah, sorry, I mixed this up. So this was off. This was supposed to be, yeah, sorry, I mixed them up. So this was, at least one of them was high to give you a low, and this could be written as, yeah, sorry about this. Yeah, this is NAND. This is AND where they both have to be low to make your output high. Sorry, they both have to be high to make your output low. So this and this is what is the inverted version of this is AND. So what we are getting is NAND here. So here again, we can write it as both of these equivalent ways of the inverted form of the inputs. All right, so questions. Let's stop here because we're going to be implementing more of these. I want you to get some feel of how we translate the behavior of transistor into digital output. We operate transistors in triode for our logic. Because that's where your zero means cut off and some voltage is where you are in the triode region.